Today we are going to discuss about buffer overflow and how it works. This discussion will be carried out in two parts. In the first part, we'll discuss about the concepts of the buffer overflow. In the next part, we'll discuss about how the buffer overflow is carried out. Now let us first look at the memory layout of the how the program runs. In the memory layout, there is stack, heap, base segment, data segment, or text segment. And in the program, there is global variables, functions, local variables, static variables, pointers, and other things. Now, global variables and static variables are initialized in the memory before the program runs. So these are stored into the either in the data segment or business segment. When the global variables or static variables are initialized like this one, this will be stored into the data segment. And this like this one, which is not initialized, this will be stored in the business segment. In case of local variables, these are dynamically allocated memories in the memory. So you see that they takes memory into the stack and continuously go towards the downside. This pointer is also a local variable, so it also takes memory into the stack. However, it points to the memory which is allocated by the malloc function by heaps from the heap by a size of int. Now this is the overall structure about how the program works with the memory. Now suppose we want to see about how the program works with the virtually or physically. Suppose there are two programs. We know that from our OS classes that various programs starts in our main memory, and since all programs it is not possible for the main memory to carry out the instructions of all the programs, so there is a necessity of creating virtual memory for virtual addresses which will address to the main memory. For this reason, you see that there are two processes, P1 and P2. They will both have addresses from 0 to 4 GB, or similarly process 2 may have virtual address from 0 to 4 GB, which is the same as main memory, but they will map differently into the main memory. But if a virtual address does not map to a main memory, there may be a crash into the program. Now let us look at the function stack layout of how the stack works. In the function void func int a and b, there are two arguments, a and b. The arguments will be reversely stored into the stack, like value of b, value of a. Then there is local variables and some addition and subtraction functions. After the arguments are stored, the return address of the calling function will be stored here. Return address of calling function means the next instruction of the calling function, and the previous frame pointer, it indicates the previous stack frame pointer of the calling function. And after that, the local variables of the function will be stored here. This is the current frame pointer, or EBP, will be stored here, and the top of the stack will be ESP, or extended stack pointer. What I meant is that previous frame pointer will have the position of the extended buffer pointer, EBP, and the top of the stack will always be indicated by extended stack pointer. The main reason why the arguments are stored in the reverse order is that when you see into the assembly language, here we see that move 1, in case of performing the addition of the x value x, the variable b is accessed, which is from the EBP, means this from this point to variable b, which will be of 3 bytes. 3 bytes means 3 into 4, 12 pointer from the EBP, this point. And again from the value of a, this will be of 2 into 4 bytes from the EBP. So these values are moved towards EAX and EDX, and addition between them is done, and these are stored into the EAX, and this summation value is then moved towards minus 8 into EBP, means this value is stored in here there is a problem. Here there is a thing that we have to keep in mind, that compiler adds random padding or random spacing into the local variables. So the value of x doesn't means that after 8 means after 8 memory space it will be stored in the memory. It means that due to the random spacing of the by the compiler, the memory address of the x will be after 2 bytes of the from the EBP. Now let us look at the multiple function, how they call each others. Now here we see that the main function calls the function foo, the function foo calls the function bar. Here this is the stack frame for the main function, this stack frame for the foo function, and this is the stack frame for the bar function. If the main function calls the foo function, the arguments of the function foo will be stored here. The previous frame pointer or EBP will be stored here, and EBP will point this, and then the local variables of the foo function will be stored here. When the foo function executes instruction for calling bar function, the arguments of the bar function will be called into this this part of the stack frame of bar. Then the previous frame pointer will indicate the next sequence of the next section of the foo function, and the local variables will be stored here. Now after the bar function completes its work, it will then return the stack pointer or ESP, the top of the stack, back to this position, and the previous frame pointer or EBP will then be reallocated to the previous frame pointer of that means the next station of the main function, or EBP will return to this position. So we see that EBP is mainly used to refer to the arguments or the arguments that are used into the function, or to call those arguments into the instructions, and the local variables are stored into the stack frame after the EBP. So all the arguments as well as local variables can be called inside a function. Now let us look at how a buffer overflow works in a normal simple program. In this program, we see that there is source, there is destination, and there is string copy from source to destination. The string copy, what it does is that it takes whatever there is in the source, and it will then copy it into the destination. However, there is a fault that can be used in the buffer flow, is that using the pointer to using pointer of the source of a memory addresses of long length, anyone can try to copy that into the destination address, and this may cause overflow into the main memory. This is because no fixed length is mentioned in the string copy or string concatenation. But in the main copy, there is a mention about size, so violation of the memory through size overflow cannot be happen in case of mem copy. And the violation I'm talking about is this one. The string copy buffer in the foo function, it takes a pointer to a string, and there is a buffer of 12 bytes long, and string tries to copy the string into the buffer. However, in the main function, if the string that we want to pass is more than 12 character, suppose this string is more than 12 character, so if we pass this string into the foo function, this will go here, and after the string copy, or here in the buffer is the local variables of the foo function. If the there is 12 chars, and since the string is more than 12 chars, so the buffer will overflow and this write the previous frame pointer and the return address and so on. So you see that the buffer overflow is occurring here. Now due to passing a long length string, when the buffer overflow of the foo function occurs, the local variables are overflowed, the previous frame pointer will also be overflowed, the return address will also be overflowed. If the return address is overwritten, so we see that when the function tries to return, it will either return to an not to a memory address that is not mapped. So in this case, the program will crash, or it will jump to a protected place where the system will automatically crash it because that place is protected, or it will try to execute invalid instruction. That means nothing will be done. However, if the attacker wants to insert some malicious code, they can also try to run those codes by violating or using the buffer overflow. Now, how an attacker will try to manipulate the buffer overflow to execute his or her malicious words? If we look here, we see that the stack frame of the foo function, where there is 12 buffer chars, previous frame pointer, return address, and others. The string pointer, that means the argument. If there is a buffer overflow, since the user is controlling the input, so if there is a buffer overflow and he can somehow manage to write the return address, so that when the input file is overwritten up to this position, he can execute a program or return address of the program that needs to be executed here. So if the return address is points to this one, so this function will continue to be executed. Now we see how one will find out the code or the memory address of this position while we want to use the return address to point to. One can do is write 0x90 or the opcode or no opcode, which means no operation will be performed, or it means that the next instruction will be carried out. Like it is mentioned, the next instruction will be carried out so that 1 minute. No function, that means the next instruction will be carried out until we reach the function the starting point of our malicious code to execute it. So rather than guessing any memory address, we use the function no-op to fill the entire buffer, so that no matter where we hit, it will continuously use the no-op function until it reaches the malicious code and continues to execute it. So this is how an attacker, if he wishes to use the buffer overflow to attack, they may use it. Now this is all about the main theory part about how the buffer overflow works and how it is carried out. We're going to go into the next section about doing the things practically and learning more about it.